For over a century, we've relied on the exact same technology to keep things cool. But there's a huge catch. The chemicals it uses are unbelievably powerful greenhouse gases. So the big question is, how do we cool our world without accidentally warming it up in the process? Well, a team at Berkeley Lab might have just cracked the code, and their solution is a completely fresh take on the science of cold.
All right, so here's how we're going to break it down. First, we'll look at the big problem we're trying to solve. Then, we'll dive into the surprisingly simple science of cooling with salt. After that, we'll do a reality check to see how it performs. And finally, we'll look at what needs to happen to get this technology out of the lab and into our lives. All right, first things first. We need to frame the problem, because the way we currently make things cold comes at a massive environmental cost, and we're officially running out of time to find a better way. You know, this really gets to the core of the dilemma we're in. As the planet gets hotter, our demand for air conditioning just skyrockets. But the very technology we use to cool our homes is actually making the planet even hotter. It's this crazy feedback loop, right? And scientists are scrambling to find a way out. And this is the real kicker. The refrigerants we use in our air conditioners today, these things called hydrofluorocarbons or HFCs, are, get this, 2,000 times more potent as a greenhouse gas than carbon dioxide. So every time one of these units leaks, and they all leak eventually, the climate impact is just huge. And listen, we are officially out of time on this. Decades of international agreements, like the Kigali Amendment, have basically put a legal deadline on phasing out these harmful HFCs. This isn't just a good idea anymore. It's a global mandate. We have to find a replacement. The only question is, what?
Okay, so if the old way is on its way out, what's coming in to replace it? Well, researchers are exploring this whole new class of technologies called caloric cooling. And the one we're going to talk about is a really cool, pun intended, and pretty unique member of that family.
So this gives you a great picture of the whole caloric cooling landscape. You've got some that use magnets, others that use huge amounts of pressure, or even high-voltage electric fields. But look at the one we're focused on today, Ionocaloric. It runs on just 0.22 volts. I mean, that's less than what a single AA battery puts out. From an engineering standpoint, that is a massive advantage right out of the gate.
So what exactly is the ionocaloric effect? It sounds super complicated, but I promise you, the basic idea behind it is something you've probably seen 100 times, especially if you live somewhere that gets snow.
Yep, that's it. It's just like salting an icy road. You throw salt down, and what happens? The ice melts. Now, that process of melting, of going from a solid to a liquid, sucks up energy. It has to pull in heat from everything around it. That's why the resulting slush is actually colder than the solid ice was. Ionocaloric cooling is basically just that simple idea, but put into a clever, continuous loop.
All right, so how do you turn that simple icy road trick into an actual air conditioner? Well, it starts with a couple of key ingredients. First, you've got a refrigerant called ethylene carbonate. And what's wild is that it's actually a solid at room temperature. You mix that with a basic salt, sodium iodide, and you get this kind of slushy mixture.
Then, you pump that slush to the part of the system that needs to get cold, like the coils inside your room. As it flows, that salt works its magic, forcing the solid refrigerant to melt. And just like we talked about, that phase change absorbs a whole lot of heat from the air. Boom, your room gets cooler.
But here's the trick, right? To keep this going, you have to get the salt back out. And this is where the real genius comes in. They use a process called electrodialysis. Basically, a special membrane and a super low electric current, yep, there's that tiny 0.22 volts again, literally pull the salt ions right out of the liquid. You're left with pure refrigerant again.
And for the last step, that pure, now liquid refrigerant gets sent to the hot side of the system, the part that's outside. With the salt gone, it instantly refreezes back into a solid. When it does that, it releases all the heat it sucked up from inside your room into the outside air. And just like that, the cycle is complete, and it's ready to do it all over again.
So that sounds pretty elegant, right? It's a really neat concept, but let's get real. How does this actually stack up against the technology we've been perfecting for 100 years? It's time for performance reality check.
First, let's just be crystal clear on the difference here. Your current AC uses a big compressor to change the pressure of a gas, which forces that phase change. This new system changes the salinity, the saltiness of a liquid to do the exact same thing. So it's chemistry versus raw mechanical force.
So what about efficiency? For that, we look at something called the coefficient of performance, or COP. All you need to know is a higher number is better. And when you look at the chart, the ionocaloric prototype is already playing in the same ballpark as a typical AC unit. For a first-generation technology, that is incredibly promising.
Okay, but, and this is a big but, efficiency is only one part of the equation. The real mountain to climb right now is something called power density. Basically, how much cooling can you get out of a given amount of the fluid? And right now, the prototype is only putting out about 6 watts per liter. A standard AC for your home needs, well, closer to 3,500 watts. That is a gigantic gap.
And if that number didn't hit home, this table will. A normal AC unit needs what, maybe 3 pounds of refrigerant? To get that same cooling power from the current ionocaloric system, you need nearly 2,400 pounds of the stuff. The cost? We're talking $12,000. It would be the size of a small car and cost a fortune. So clearly, that's not going to work.
Okay, so at this point, you're probably thinking, well, that's a deal breaker. Fun experiment, but it's over. But hold on. The researchers know exactly what the problem is, and more importantly, they think they have a clear path to fixing it.
The whole problem, the entire bottleneck comes down to one single part, that membrane we talked about, the one that separates the salt. See, they're just using a generic off-the-shelf membrane that was made for desalinating water. If they can engineer a new membrane, one designed specifically for this refrigerant, they think they could boost performance by a factor of 1,000, maybe even 500. And just look at what that does to the numbers. Suddenly, your 2,400-pound system is just 4 pounds. Your $12,000 cost plummets to 24 bucks. It completely changes the game.
But at the end of the day, it's always going to come down to this, isn't it? The science can be brilliant, the environmental upside can be massive, but if it's going to succeed in the real world, it has to win on cost. That's the ultimate test.
Which kind of leaves us with this final big picture thought. Making heat is simple. We've been doing it since we discovered fire. But making cold, that's hard. It's all about moving heat from one place to another. For more than a century, our best solution has involved these complex, high-pressure systems with planet-warming side effects. So you have to wonder, could the real breakthrough, the simplest solution, have been right in front of us this whole time? In the simple chemistry of salt and ice.